Akash Banerjee from IIT Bombay. So Nikhil, the stage is yours. You can start.
Thank you, sir. Good afternoon, everyone. I'm Nikhil Saini from IIT Bombay, final year MTech student. So let's start. I'll share my screen. Is it visible?
Yes, sir.
Yes, it is visible.
Yes, sir.
Okay, thank you. All right, so I'm working under Professor Pushpak Bhattacharyya, and this talk will end by his comments on machine translation, and I'll be beginning the talk. So my topic would be on disfluency correction in the context of speech-to-speech machine translation. So, yeah. So let's start with a motivation to the problem, where how disfluency plays a role in doing machine translation. So in India, the number of languages which are spoken today are 415. The languages which are spoken by more than 10k speakers are 121. Those with more than 100k speakers are 60, and the languages which have more than a million people speaking today are 29. Now, accounting to these, the number of individuals who can speak but can't read or write their language, so they are illiterate, they can speak but they cannot make use of reading or writing. There are 300 million people. And if we take some liberty, these are also the number of smartphones which are currently being used in India, 300 million. So this data tells us the need of speech to come into the picture, and only text-to-text machine translation cannot serve the entire purpose. And therefore, we need to account all the irregularities and problems which pertain to speech data, that is audio files, and the systems today which are being trained on text-to-text data on machine translation, how do they affect and how much they are affected when speech comes into the picture. So speech can come into picture directly as an audio file when we speak, like to Amazon Alexa, Google Home or Siri, or they can be transcribed by an automatic speech recognition system, and that text can be given to the machine translation system, which works on text to text. So speech is well rehearsed, or it can be conversational. So well rehearsed is like when you see news anchors or in assemblies or in courts, whereas in conversational, like I am giving a talk right now, we normally talk to each other, or with a telephonic conversation. These are all conversational speeches which are spontaneous and prone to disfluencies present in them. Whereas text is well formed and formatted. All the notebooks, books which you have read so far, the official documents, Wikipedia pages, everything, a letter which you write to a boss, everything which you write, you can press the backspace, delete all the irregularities which are present, and make a well formed statement, and then you send it. So the text data which is present on web is well formed and formatted, and there is less disfluency present in it. Now, this mismatch between speech and text data need to be taken care of, because all the machine translation systems, be it in any language, are trained on this well-formed textual data. So I'll just take the pointer. So when you give a conversational data, which is the transcription of speech or a speech file, to a model which is trained on well-formatted data, the output is not as expected. I would like to request you to recall, if some of you might have seen a machine translation system. If not, you can go to Google and search the already available systems. A small full stop, exclamation mark, comma, apostrophes, question mark, a small change can change the entire translation output. When these small irregularities in the systems which are being trained on text to text make such a vast difference, then imagine how much the speech or conversational data will make. So to more alleviate the problem, let's look at this figure. Here we have automatic speech recognition system to which an English disfluent file is given where the speech is disfluent. Like suppose I'm talking to you right now, there are a lot of filled pauses. Like I'm taking o, uh, mm, I'm taking breaks, and there are certain terms which I might delete. I might say that, oh, this is wrong, and I was supposed to mean this. Now, these intermediate interjections, interruptions are all different. So, the automatic speech recognition system will transcribe the speech as, well, I was eating oh, bread. Oh no, grapes. So this repetition of words, the fillers being present here, and then the correction of bread to grapes, these are all disfluencies. Now, if you give this transcription to a machine translation system, it will not produce the expected output. The input which it was expecting was, I was eating grapes. This kind of a text can be given to a model, and it will be producing the good output because it is trained on such data. So it will mimic that data. Now, our task is to remove these disfluencies from this text so that our empty model can work properly. So you can consider this task of correcting the disfluencies present in speech as a pre-processing tool, or you can do it in an end-to-end fashion where end-to-end model will take care of this in itself. So a lot of work has been done in detecting disfluencies, and very recent work is done in correcting disfluencies, and no amount of work is done in end-to-end fashion up till last year. So we have tried to handle this problem in both the context of machine translation and English to English, disfluent to fluent tasks in two papers. So let's look at this one. Here, this is what the task is about. That is text to text disfluency correction, and I have pointed out already that the fluent output should be I was eating grapes. Now, again, the same problem lies with this task. As you may ask what the problem is, we can give it a sequence to sequence model, and then we can have a model which will correct the disfluencies. But again, the problem is paucity of parallel data, which is from disfluent to fluent. So in English, we have very little data, and imagine how little would we have in other languages. We are working on this problem, and we do not have the data for Indian languages. So there is a immediate requirement of handling this situation by other means of machine learning instead of going through collecting and manually creating parallel data sets. So the first task is to understand what is disfluency. So I'll give you an example, and then I'll talk about the surface structure of it. So consider this example. Well, we are actually getting ready. Here, well in green is a discourse marker. We are actually, so this VR is a repetition in red. Actually is again discourse, and is an filler word. So the filled pauses are like oh, these kind of. And the fluent one would be we are getting ready. So let's talk about the surface structure of disfluencies. So it consists of three parts. One is referendum, then is interruption point, then comes an interregnum and repair. So every sentence can be broken up into these parts. And when we talk about the surface structure, we are not giving importance to simpler disfluencies like filler words, and we are only talking about complex disfluencies. So what is referendum? So referendum contains those words which are originally not intended to be in the utterance. So this actually was not intended to be in the utterance. Therefore, it will consist of one or more words which will be repeated or corrected immediately. So, like in the previous example, which you might see, or on this page only. So it says three flight tickets to Boston. Now two tickets is corrected to three tickets. So this is immediate correction. This yellow part is referendum, and it is being corrected here. So the referendum contains those words or phrases in the utterance which are not intended and are supposed to be repeated or corrected immediately in the repair part. So this consists of false starts. This is an example where this was false and it is corrected here. So it is corrected in the repair section, which is green. This is the interruption point. At the interruption point, the referendum ends and the integrum starts. In the integrum, there are filler words and other phrases which are supposed to be taken care of easily. The fluent sentence for this would be, I want three flight tickets to Boston. Now the task which you should keep in mind is to convert this disfluent sentence to fluent sentence. So this is the surface structure where in every sentence you can see the referendum, integrum and repair being present along with the interruption point. Here all three are present. Here interregnum is absent, and here referendum and repair both are absent, and only interruption point is available, which consists of filler words, discourse markers like well, and all of that. So this sentence would translate to how about next week. So we are done with the surface structure of the disfluencies. Let's talk about disfluency types. So in this slide, we have 6 of them being classified as filled pauses. So filled pauses are non-lexicalized sounds with no semantic content. Example being this, which I've already pointed out to. The one sentence would be, we are getting ready. And you may notice a lot of that being present in my talk, which I'm giving right now. Interjections. Interjections are the part of speech that demonstrates the emotion or feeling of the author. So when you say oops, gee, these kind of things are interjections. They do have some semantic meaning, which when a speaker speaks are conveyed to the listener. So I dropped my phone again. Oh, so this do have a meaning, and this is called interjection. Now comes the discourse markers. These are the linking words and they do not contribute to the semantic content. So, has a semantic meaning. It is grammatically correct, but it is not required to complete the semantic of the sentence which are supposed to be spoken by the speaker. So, well, I'm going to America. So this well is a discourse marker. This is, a pretty good sport. Now, to elevate the importance of, or to recall how often this is spoken, this is being heard is, you, some of you who are interested in sports, you may have heard the post-presentation ceremonies of Mahendra Singh Dhoni and other cricketers, and specifically talking about MS Dhoni, you may have heard that their every sentence starts with and every sentence starts with an ends with and. So these kind of discourse markers are very much spoken by people when they are being conversant. Then comes repetition. So repetition is exact repetition or correction of words which is previously uttered. So this is exact repetition. This is a bad situation, and people do often uh, take up this disfluency very often. Another one which is correction of words was in previous slide, where two tickets were corrected to flights. Then comes false start. In false starts, we start a sentence with something, then the speaker realizes, oh no, this was not what I was supposed to speak. So he stops there and then speaks a different train of thought. The example would be, we will never find a day. What about next month? So after a day, he realized that he was not supposed to speak this. He totally discarded his the beginning of the sentence which he uttered, and spoke a different train of thought. In repetition, there is repetition of phrases or words, but that is in the same line of thought. Here, the line of thought is changed again. So the fluent one would be, what about next month? Now the most complex one would be edit. Here the phrases refer to the words which are just previously have been said, indicating that they are not intended to belong to the utterance. So see here, we need three tickets for the flight to Boston. Now this two tickets needs to be edited and converted to three tickets. So this is how disfluencies are being classified in the literature survey, and people have been working on these to analyze what is the pattern of them and how do they occur in disfluent text and speech. So these are again just some other examples which you may later see when the slides are being sent to you. That he might is a restart, because you see that he might is here. Is a filler. This is a discourse marker. Then VR is again a restart. Actually is discourse or is filler. So I mean this is an edit term. It is completely none. Then this is again another disfluency. So being done with these disfluency types, we will now have two tasks which we will be trying to solve. So for these two tasks, we have our publishing. The first one was published last year in IWSLT 2020, and the second one is accepted today morning in EACL 2021. So this is you are given a disfluent text in one language, say in Spanish, and you have to remove the disfluencies as well as translate it to English. So it is not simple as uh, translation from language A to language B. Doing the task along with it, you have to remove the disfluencies present in language A. So this was a task presented in IWSLT 2020, and we will see how to correct this. The other one being to correct disfluencies present in the same language. That is, I give you an English sentence, you give me the fluent English one. Now, this fluent English
S-
sentence is someone.
yes, sir.
Yeah,
Doubt.
yeah.
So my doubt was just if the disfluency is a sentence like I need two tickets and one more. So the edit would be sort of plus one, right?
Uh, your sentence is I know two tickets and one more.
Yeah. So it's like the word three didn't come, but the meaning is three. Is that possible?
No,
Like, uh,
no, no. This is not disfluency.
okay, okay,
This is correct.
okay. That's not okay. Thank you.
Yeah. So we do not. We are not. We try to avoid paraphrasing.
Okay,
So
okay.
disfluency correction is mostly
Mm,
99% removal of words. You do
mm,
not paraphrase them, you do not add new terms, you just remove the unnecessary terms.
mm,
And the aim should be that by removing them, grammaticalness should be maintained
mm,
and this meaning which the speaker intended should be
mm.
conveyed.
Okay. So here that would not be a disfluency, that would be a part of the sentence.
Yeah, right.
Okay. Thank you.
Okay. So, yeah. So, we will take a look at the first approach, which is noise induction. And this is a synthetic data generation technique, which was which was experimented in India in 2018. So what is this disfluent reference in Spanish here? So you see this is disfluent where you can see this is repetition, and we have to convert this or do a machine translation to English language, but we have to remove the disfluencies as well. And the problem is that we do not have much parallel data. So how do we obtain this text? We take telephonic conversation, apply automatic speech recognition system, get the text, and then we do this processing. So this is from disfluent Spanish to fluent English, but it is text to text. We have not yet reached the speech domain. So I hope the task is in mind and we can now deal with this. So the task is text to text. These are the data files which we have, that is disfluent speech, their disfluent transcripts, the ASR output, which is disfluent, the disfluent translations, and the fluent translations. So we do have both disfluent translations and fluent translations. Now, ASR output is disfluent, and we do have fluent translation. So this is a parallel data set, right? So we can give it to a sequence to sequence model and train a disfluent to fluent model, and we can get a good system. But the task was not about this. You cannot make this use of this fluent version on the target side, and you cannot train a sequence to sequence model. Otherwise, it would be very easy and anyone can do that. So this is given just for reference or calculating blue scores and other metrics. What we have to do is we have to take this only two blue boxes, the disfluent input and the disfluent output. And now with no single reference to the fluent domain, you have to remove the disfluencies and convert Spanish to English. So this was the dataset, which is Fisher dataset. It is not freely available. It was given to the participants. So there were around 1,38,000 different sentences in Spanish, which were having their corresponding English disfluent sentences. Just remember that there is no fluent English sentence available for training, so this will be an unsupervised setting. Now we have made use of, since this is an unconstrained setting, we can make use of other corpuses. So we have taken news commentary corpus, which is again having 87,220 sentences, and this is fluent. So with this data set and the setting in mind, we can move ahead. So the approach would be to synthetically generate parallel data. So what we do is we take the news commentary corpus, and the idea goes like this: the news commentary corpus is fluent. Why not let's add something to it to make it disfluent and mimic the disfluencies present in English? So this will be kind of something like this. We have Fisher corpus, which is English and Spanish, both being disfluent. We take the news commentary corpus, we have the fluent sentences, add disfluencies to it, we have the corresponding disfluent sentences, and this will be a English to English, disfluent to fluent parallel data set. So this would be, I want to book 2 flights. Oh, sorry, 3 flights to Boston, and this is, I need to book 3 flights to Boston. So we already had this. I need to have 3 flights to Boston. We added the disfluent terms by some measures, which I will discuss in the future slides, and we have a pseudo parallel data set, which is from English to English. So how do we create such data set? There are few techniques, out of which 4 I have stated here. Others you can go and read in the paper. I'll put a link to that. So you make use of the uh, sentence structures which is present in the disfluent data set. So one is pronoun phrase repetition. You know, so all the sentences which start with the pronoun, these are very very simple techniques, but they turn out to be very useful. So the sentence in the news commentary corpus was, I am fond of paintings. Now this starts with the pronoun, and you can repeat the phrase I am. So the fluent one was, it is cold and windy outside. You can take this it is cold and repeat it. Now how much you want to repeat depends on you. We had a random number generator which repeated the phrases from a length of 1 to length of 4 based on some distribution. Like more weightage was given to length 1 and 2 and less was to 3 and 4. So this is an example where original one is, I was saying that we should go for a movie. Now it starts with a pronoun. So this can be a simple Python script where you can take all the sentences and repeat the phrases. So when your random number generator gave you a length of 1, you repeated the phrase I. It gave you a length of 2, you repeated the phrase I. Similarly, in fluent phrase repetition, the original sentence is this. In this sentence, by some measures, probabilistically, you pick an index, say index 5, you reach in, and then you get a random number generator of some length based on some probability distribution, which needs to be hyper tuned. So we get a length of 1 and we repeat this phrase. Here we get the index 3, we reach and we repeat a length of 2. So and speculate. So this becomes fluent, and this is the corresponding disfluent. In false start, this is a very very lame technique. False starts are not generally of this type, but we try to make more and more data. So all the sentences we start with a yes, we try to append no of length 1 or 2 or 3, and all those which started with a negation, we try to append yes in the beginning of the sentence. Now there is another type of disfluency which is filler words. So what we do is we have a set of fillers from the disfluent data which was given to us. So you take the disfluent data, count the phrases. So was present 23 times, 233 times. Was present, say, 457 times. Now is present in the dataset 5,000 times. So with these frequencies, you can make a probability distribution, give the weights according to the frequency, and fill these phrases into the news commentary fluent corpus to make disfluent sentences based on the proportion of their frequencies, and you obtain the disfluent sentences at some index. Now these index are supposed to be not at the end for this particular disfluency. They are generally at the beginning or in the middle, if you remember the interregnum part. So in this way, we apply these techniques and some more to obtain a pseudo parallel English to English, disfluent to fluent dataset. Now, what is the architecture? The architecture would be for a simple machine translation, you need an encoder and you need a decoder, which is Spanish to English. Now, you want to do disfluency correction as well, right? So, if you have attended the talk on 8th, I have talked about the denoising autoencoder and back translation. So, both play an important role here. So, see this noise. This is the noise which we add to a denoising autoencoder. So, how do we remove disfluencies? We treat the disfluency present in the source sentence as a noise, and it is the decoder is supposed to correct that noise. Can I pick it? Yeah. The decoder is supposed to correct that noise and give the fluent sentence. We have the cross entropy, sum of token level cross entropy loss function here, which is then backpropagated. So what do we do is we have two data sets. One is disfluent English to fluent English, which we have created synthetically. The other one is disfluent Spanish to disfluent English, which was given to us. So we give our pseudo parallel dataset here. Disfluent English is given here from news commentary corpus. It goes to this via this encoder. We get a latent representation here. We give to this decoder here, and it is supposed to predict the fluent one. And whatever the loss is, backpropagate this. In the same epoch or iteration, we take the disfluent Spanish sentence, give it to the decoder, get the latent representation of the encoder, give it to the decoder, and now tell the decoder to generate fluent English. So it generates something in English, which is then compared to the disfluent English sentence which we have. So the upper one is doing the task of disfluency correction removal, and the lower one will allow us to learn Spanish to English, disfluent to fluent. Now the trick is that we share this encoder, this decoder. So the decoder learns both translation from Spanish to English as well as disfluency correction. And in the encoder side, we keep one layer separate and the initial layer shared, so that the separate layer would allow it to store information related to English and here to Spanish. So this architecture was used by us. The number of layers which you need to share and which you need to keep as held out need to be hypertuned, and we have those mentioned in the paper. These were the results. So alpha is the amount of noise which you want to induct, right? So you can induct huge amount of noise to make your pseudo parallel dataset, and you can induct very less noise. So consider a random number generator which generates two numbers 0 and 1. If it generates 0, you add disfluency to the current sentence. If it creates 1, you do not add. Kind of this. So it depends on the alpha, which is 0.5, 0.3, and 0.1, which translates to how much disfluency we have added to create a pseudo parallel dataset. And these are the results which we get on a single reference and double reference on Spanish to English, disfluent to fluent translation. And our paper was accepted last year, and we got on their held out set a 28.1 blue score, which was the highest on ASR output. So this is on their test set which was given during the competition. So this is not very important for you, but the technique which is used to remove the disfluencies as well as translation is very new, and can be used to incorporate this idea in other tasks. So with this, we are done with our first task, which is translation from one language to another, and while incorporating other submodular tasks, which is because of the inherent nature of spontaneous speech. If anyone has any doubt, this is the right time for this task. I'll wait for 10 seconds. Okay. Right. Okay. So we'll move on. So if you remember the second task, it was on correcting disfluencies in English and no translation. That is, suppose you have an empty system which is already trained from English to some other language, say Hindi, and now you want to give it the output of an ASR system which is disfluent, but you want to correct it as a pre-processing step. So you don't want to integrate the disfluency removal step in your model because your model is superior and doing very good and you don't want to touch it. So what you can do is you remove the disfluencies present with a different model as a pre-processing step and give the generated output to your pre-trained empty model. So this is the task from disfluent English to fluent English. Now here uh, we borrowed the ideas from our previous paper, which I just described, uh, that we can create a pseudo parallel dataset in English and train a system from this is the pseudo parallel dataset, which is created by adding noise to the fluent sentences and disfluencies properties are being extracted from the disfluent corpus. We give it to a simple sequence to sequence encoder decoder architecture and we get some result. But surprisingly, this supervised training by having a synthetic generated data didn't turn out well. And this was one of the approach which we tried, which can be applied to this particular domain. Now, other one is unsupervised and semi-supervised learning. And let's have a look at it. So this will be completely new thing. So in 2020 ICLR, there was a paper, a probabilistic formulation of unsupervised textile transfer. Sorry, this was in ICML, not ICLR. Okay. So what they do is they handle the task of style transfer in a completely unsupervised manner. So style transfer can be from different, can be understandable in different domains. Like you go from informal text to formal text, or this technique can be applied to machine translation also, like from one language to another language, and there are many applications. So we try to adapt this to our setting, that is from disfluent to fluent. So what this diagram shows is that x bar is the latent variable, y bar is the latent variable, which is hidden variable. Y and x in green are observed variables. This is a shared encoder decoder architectures, so don't get confused with so many encoders and decoders. There is only one encoder, there is only one decoder. We have just tried to present it for clear representation and understanding. So what do you have? We have disfluent English sentence and fluent English sentence, but these are not parallel. So suppose I give you conversational data set, which is disfluent, and these are 1 lakh sentences from people speaking in America. And now I give you some Wikipedia data, which is fluent, which is scraped from the web, and this is why. So these are not parallel, therefore the system is unsupervised. Now, what do we do is we try to create a hidden representation which is supposed to be in the other domain. So, if this is fluent, the corresponding disfluent will be the latent x bar, and if this is disfluent, the corresponding latent would be the y bar. So, for these two unparalleled datasets, we tried to create their corresponding counterparts. We do not uh, generate the text, but we train the model such that it has an hallucination that they are present, and we treat them as a latent representation, which is then used to train the model in an unsupervised fashion to solve this problem. So, how does this work? Is uh, suppose we go from this side, you have a disfluent sentence, which is a spoken utterance. You give it to the encoder decoder, and you tell the decoder that, okay, I'm giving you an disfluent input, give me the corresponding fluent one. So, how do you tell this? You give it a embedding. So this is a kind of signal which I'll describe in the later layers, which is obtained by a pre-trained classifier. So for the moment, consider that it is a signal which is telling that take a disfluent sentence, convert it to the fluent one. Now, when this fluent one is generated, it is again given to the same encoder decoder, and now we tell that, see, you got a fluent sentence by this signal, and give me back my disfluent sentence. Now, when this cycle completes, you have a generated, synthetically generated disfluent sentence, and you compare it with your original disfluent sentence and calculate the cross entropy loss. So, this is called as reconstruction loss. Similarly, we will do this for the fluent domain, and we will get a complete cycle, calculate the cross entropy loss, and backpropagate. So this is the idea, and there are two steps. Denoising autoencoding is there, and this one we call as back translation. Now, for those of you who are interested, there can be different techniques which are applied. That is, you can backpropagate only to this from x to y bar, or you can complete the cycle for backpropagation. And these kind of tricks you can see when you train a model and when you're doing some research. Yeah, so we have tried both. So let me first describe what this pre-trained classifier is. So when you have a data set which is disfluent, you have all the disfluencies marked with it. For every sentence, you have whether it is filler, conjunction, discourse, repetition, and all that. So you train a CNN-based classifier on this disfluent set, and you get the embeddings of it. So see, this is the output layer, which will give the prediction whether the given sentence is filler, conjunction, or repetition, or other disfluencies. So when this system is trained on the loss function, now this has a accuracy of 92%. So you take the penultimate layer. This penultimate layer of the classifier will work as an embedding. You all might be aware of word embeddings. So this is kind of the representation or the sentence embedding of the disfluent sentence and the fluent sentence. So the disfluent embedding will tell that, see, this is a disfluent sentence which is being given to you as an input. Now give me the fluent one. So this is how we get the disfluent and fluent embeddings from the pre-trained classifier, which works as a signal for the encoder decoder architecture to tell it in which direction it should go. This is again an example describing the same architecture but with examples. So this is the disfluent sentence. Oh, it's an apple, which is given to the encoder decoder. It is telling, see, you have to convert it to fluent. So it converts it to it's an apple. In the very first iterations, if you go to your code and print, this will be something really rubbish and not meaningful. But I've tried to put the correct version here. Now this will be again given to the same encoder decoder with the signal now converted back to the disfluent one, and you'll get something, not this, but something. Ideally, you should get this. You'll calculate the loss function here and propagate all the way to the initial stage. And similar in the other side. So this is done with the disfluent dataset. This is done with the fluent dataset. Both are different. One is of American speakers. One is the Wikipedia data. So you do not have any parallel dataset. Keep that in mind. Now, what we have done is, so this was our adaptation to their proposed approach for disfluency correction. Now, their this signal can be binary, you know. So you can give one to it, it will understand it as fluent, and when you want to say disfluent, give it a zero, like a vector of zeros or a vector of ones. But to since we have disfluency marked dataset, we thought of why not give the exact signal to it. So what do we do is in transformer architectures, which will be explained by Akash, how transformers work. So see, this is the input to the transformer decoder, and every time step it expects the input as 1024 dimension. Now we have our word, which is the previously predicted token, which is again 1024 dimension. But we have our domain embedding as well, this signal of disfluent and fluent, which is 512. So how to give this to this? One simple technique would be addition, which is totally useless. Never do addition of two vectors and give it to a model. So what we do is we do this demonstrative reduction applied by some matrix multiplications here and activation functions. Then it is reduced to 512, and we append this to 512 to make a 1024 vector, which is then given to the decoder. So it has both the information of embedding type and the previously uttered token, and it predicts the next token. So this is how we introduce the domain embeddings. Now, along with this back translation step, the denoising also takes place simultaneously, where the input batch is given, noise is added to it, given to the encoder decoder, and the output is then compared with the fluent one or the input, and the reconstruction loss is calculated. And this is only done for the fluent sentences. So, denoising and back translation. Now, in both the talks, the one on the 8th and today, the denoising part plays a very crucial role. So, we'll discuss shortly how disfluencies how this denoising works in denoising autoencoder. So, one aspect is the word blank. So, what do we do is in the given input sentence, we blank a particular token. So we create the probabilities uh, from a probability generator model, which gives us uniform distribution from 0 to 1. And the one with less than some threshold, which is C 0.23 and 0.17, less than zero point 0.5 here, we blank these tokens and we give this to our model, and it is supposed to generate the original one. This is one kind of noise which you can add. The second one is this, where word drop out. So these words are dropped. And in the third one, this is word shuffle. So you get the index, get the probability from uniform distribution. Now we don't want to trick the BOS, so we set this to 1. This will not be misplaced. And here we get the scores by adding noise and index, and these words are shuffled. 3 comes here, 2 comes here, and the new sentence is I went to I too went the market. Now this shuffled sentence is given to the model, which is supposed to recorrect this noise which is added to it. So these three kinds of noise are given to a denoising autoencoder in machine translation systems. So the model architecture which we have used has these parameters. These are irrelevant as of now. Only if you're interested, you can have a look at them back again. We'll discuss the results now. So these are the Skyline models. They take the parallel dataset, which is disfluent English to fluent English, and you see BART is a denoising based architecture, which is sequence to sequence pre-training for neural language, natural language generation, translation, and comprehension, and this achieves 90 blue score. And this is a sequence to sequence BiLSTM which achieves 88.08. Our noise induction achieved 53 blue score, which is pretty low, and our approach didn't work on this task. So we took style transfers approach, which is unsupervised. A BiLSTM model achieved 62 blue score. We thought that this might be the limitation of the BiLSTM architecture. We used transformer. We got a blue score of 79.39 with the domain embeddings from the pre-trained classifier. And now comes the semi-supervised part. So see, with no parallel data, this is 90 and we are almost 80. So now our goal is to improve this number. So how to do that? So what we do is we reach into the pool of semi-supervised learning and we take 1% of the parallel data. So we take only 554 parallel sentences, which is disfluent to fluent, and we fine tune our unsupervised model with this 1% of data, and we see a jump of 5 to 6 blue scores from 79 to 85. Now, if you give 100% data, this is 88.22. So this is very significant. Only with 1% of data, you have a blue score of 85.28, which is very close to 90.08, which requires complete supervision. Now, this paper uh, was published or submitted to EACL 2021 and has been accepted. I will try to make the preprint available and give it to the organizers, and you can have a look at that if you're interested. These are the blue scores which are available for particular disfluency types to do the analysis of each disfluency for all the models, and this can be looked up again if you're interested. This is the output analysis. So see, the unsupervised BiLSTM is failing here, but BART and sequence to sequence models, which are on complete supervision, are giving the correct output, as well as our unsupervised and semi-supervised models. This example we have deliberately put to show that since you're using complete supervision, they are somehow better than our unsupervised model, but that's not a lot, and we are very near to it, which is equal to the fluent one. So more examples are present in the paper. You can have a look at that. This is a web service which is present online. Um, this gives you just a demo. I'll give very quickly. Test fluent English. If you give here and you translate, so this will give you the fluent output. Yeah. So these are all the disfluencies which are present. See, this is repetition. This is filler words. This is repetition. This is conjunction followed by repetition. And use this. So this conjunction and the
So your voice is very low.
hello. Yeah, is it
Now it's okay, sir.
so? Was I not audible for the last 5-10 minutes?
Sir, it was little. It was very low audible.
Oh, you must have told me earlier. So was it like
No, it's
very?
just two. It's just past 2 minutes. Not an
Yeah.
issue. We heard
Okay.
you.
So should I continue or should I repeat something?
No, I think you can continue. If
Okay.
someone
Oh.
has problem, then they can raise your voice.
Yeah, please ask any doubts. Yeah. So this is how the conjunctions and repetitions are handled here, and I'll not give and go through all the examples, but this the backend is our model, which is semi-supervised one, which is right now being used here. So yeah, this is how these two tasks are handled, and thank you. I'm welcome for the questions. Okay, I see there are. I think we can go on, Raj.
Okay. Thank you, Nikhil, for the wonderful session. We
Yeah.
will now switch gears and move towards Akash. So, Akash, you can start your presentation if ready.
Hello, am I audible?
Yes, you are audible.
Thank you, Raj.
Um, is it unshared or is it being shown right now?
It is unsaid.
Done.
Your screen is unsaid, Nikhil.
Thanks. Okay.
So, is my screen visible?
Yes, Akash, go ahead.
Okay. So, hello everyone. I am Akash Banerjee. I am a MTech student at IIT Bombay, and I am doing my project under Professor Pushpak Bhattacharyya. Today, I will be mostly talking about from basic neural networks to recurrent neural networks, and then I will also talk about transformer a bit. It is the state of the art model now. And so let us begin. So this slide shows us the perceptron model. So a perceptron model basically is a supervised learning model, which uh, hello, am I audible?
Yes, sir. Yes, sir.
Okay. So as we can see in the diagram, the perceptron model takes n inputs, and with each input it has a weight associated with it, so w1 to wn, and after it does the weighted sum, so this means w1 into x1 plus w2 into x2 and so on, it passes it through a step function and gets the output. So the perceptron model is motivated by the biological neuron, and it can be described as a single layer feed-forward neural network. So what is this step function? Let us see. So step function is very easy. It is implemented as if the weighted sum of the inputs is greater than 0, then the output is 1, and if the otherwise the output is -1. We see a diagram here for threshold theta, the value is 1 and otherwise it is -1, and this threshold theta is generally taken as 0 here. So some points about perceptron. So a perceptron is generally trained using the perceptron training algorithm. So in perceptron training algorithm, the weights are at first randomly initialized, and it is an iterative algorithm. In each iteration, the value of the weights are slightly changed, and the algorithm continues till we reach convergence. So the perceptron is a linear classifier and can represent all primitive Boolean functions like AND, OR, NAND, NOR, etc. Linear classifier basically means In a 2D plane, a linear classifier can classify points which are on two sides of a line. In a 3D space, it will be a plane and so on. So for non-linearly separable functions like XOR, perceptron fails or a single layer neuron network fails. So we need to add further layers in the network to represent XOR, the XOR function. So in this slide, we see a basic feed-forward neural network. It as inputs, it has x1, x2, and x3, and it has two hidden layers, h1 and h2, and in the output, it has two neurons. So the number of hidden layers can be very large in number, and also the number of neurons in each layer can be very large. That is why we often hear the term deep neural network or deep learning. And at each of these blue boxes, sorry, the spelling of blue is wrong here. So at each of these blue boxes, an activation function is applied. So basically, as input, we give the weighted sum of the weights like W1 into X1, W2 into X2, W3 into X3, and so on. And also a bias term is added. And an activation function is applied like ReLU, sigmoid, or 10H to introduce non-linearity. We will see what non-linearity does in coming slides. And the backpropagation algorithm is used to train the feed-forward neural network. It is a very popular algorithm, and you can check that out online. And so what are activation functions? Why are they used? So as I said, activation functions add non-linearity to a neural network model. So before each layer, the inputs from the previous layer, a weighted sum of the inputs of the previous layer is taken and fed as input. So if no nonlinearity is introduced, then any big multilinear feed-forward neural network will be identical to a linear classifier. So this is because if no nonlinearity is there, we will be just taking weighted sum of the inputs and doing that over many layers. So it will not be much different from a perceptron. That is why we use activation functions. Another application is that they also help in keeping the output values from a layer restricted to a certain limit. So if we do not do that, then the values can explode, like it can reach very high numbers and cause computational problems also. So in this slide, we see some commonly used activation functions. The oldest activation function is maybe sigmoid. So it is basically fx is 1 by 1 plus e to the power minus x. We often see sigmoid function in logistic regression also. It basically squashes the value of x to some number between 0 and 1. Another activation function is 10h. So this also squashes the value between a number from -1 to 1. The most commonly used activation function now is ReLU, which is rectified linear unit. It is a very easy function, as we can see. And if the input value x is greater than 0, then it is just a linear line, otherwise it is 0. So ReLU is very popular now because it is very easy to compute, and its differentiation is also very easy. So differentiation will be 1. And as the backpropagation algorithm uses the gradients at each point, the cost of differentiation is also a big factor. Another modification to ReLU, which is leaky ReLU, is sometimes used. So instead of, when the value is negative, instead of taking 0, we take a small number like ay. So here a is generally taken as 0.1. So the slope is very small. And in backpropagation algorithm, the errors are basically backpropagated. So we see two loss functions here, which are used to calculate the errors. One is a total sum squared error, and another is cross entropy loss. So sum squared error is very easy. T1 is the target output, which means we should get it as our output, and O1 is the observed output, which we get from the neural network we are training. So basically the difference is taken and the square is applied. Square is applied because the difference can be negative and positive both. So we do not want them to cancel out, and hence square is taken. Here it is summed over n, which represents the number of layers in the number of neurons in the output layer, and p is the number of training examples. So basically we are taking the sum of errors over all the training examples. And cross entropy loss is another error function, which basically computes the error between two probability distributions. So here y1 is the target output and y1 star is the observed output which our neural network gives. So in case of machine translation, yi will be a vector of length equal to the target vocabulary size, and as each step we expect only one word as output from our neural network. So it will be a vector of many zeros and only one, many zeros and one, one. And y1 star is the observed output. So it is basically a vector which is also of target vocabulary size, and the sum of its values is 1. And we generally see cross entropy loss function in neural machine translation. So this was mostly about feed-forward neural networks. You can check out the backpropagation algorithm online. I have not described it here. Next, we move to recurrent neural network. So recurrent neural network is basically when many neural networks work and depend on one another. So this is because in a sentence, when we are predicting one word, the word generally depends on what words are also present along with it in the sentence. The inputs are not independent of each other. So a recurrent neural network is basically the same architecture we see on the left. We give as input X. In the hidden layer, we get S, and as output, we get O. The U, V, and W are weight matrices, which are calculated using the backpropagation algorithm. And in the right, we just see the same network, but it is unfolded. Like at step t-1, we get an output. The hidden state at t-1 is fed to time step t, and so on. So this slide is basically about the notation, where xt is the input at time t, and ot is the output at time t, st is the hidden state at time t. So how st is calculated is using a function, and it is a function of the input at time step t xt and also the hidden state from the previous time step st-1. As I said, UVR matrices of weights which are learned, and backpropagation through time algorithm is used to train a recurrent neural network. And it is a modification of the backpropagation algorithm in feed-forward neural networks, where a time component is introduced. F is a function of the input and the previous state, and as F, we generally use 10H or ReLU, which we already saw in previous slides. And OT is the output at time step t. So OT is generally calculated using a softmax function. We will see the softmax function soon. So let me first talk about the softmax function. So what happens is the output from the recurrent neural network is a vector of values. So the vector size is the target vocabulary size, as we talked about it. And to convert this output layer vector into a vector of probability, softmax activation function is applied. You may have already heard about it. So basically at the denominator, the power, these values are raised to the power of e and added. So at the denominator, it will be e power 1.3 plus e power 5.1 and so on. And at the numerator, e power 1.3 is placed. So This is basically e power 1.3 by the denominator gives 0.02. For 5.1 it is 0.9 and so on. So we basically apply the softmax function to convert it into the probability distribution, and this is used by the cross entropy loss function. So some points about RNN is that RNN shares the same parameters across all the steps, the UV and W. So this greatly reduces the total number of parameters we need to learn as the parameters are shared over time. And also sometimes the output at each time step is not needed. For example, when we are trying to calculate the sentiment of a sentence, after parsing the whole sentence, we can give a sentiment like positive or negative. We do not need to give it at each time step. So this slide talks about some RNN extensions. One of them is bidirectional RNN. So bidirectional RNN basically means we there are just two RNNs stacked on top of each other. So this basically means we in one of the RNNs we parse the sentence from left to right. In another RNN we parse it from right to left, and we combine the hidden states at each time step. So this the idea is that the output at time t may depend not only on previous elements but also on future elements. So this means to predict a word at any position, we may have to look at words which have come before it or which are after it. So bidirectional RNN basically does that. And two other variations of RNN, long short-term memory and GRU, are used now. They are extensions of RNN in the sense that they solve the problems like of long-term dependencies or vanishing gradient. So long-term dependencies means that if we give a very long sequence as input, then when we go towards the end of the sentence, we may forget what we saw in the starting of the sentence. So LSTM tries to overcome it, and you can check out what LSTM does in more detail in the blog I have linked. I will not talk about it here. And GRU is also very similar to LSTM, and you can check out the blog here for more details. I will not talk about it here. So neural machine translation, we will now move on to it. So neural machine translation basically uses recurrent neural networks, which we saw earlier, and it uses encoder decoder mechanism where the encoder is a recurrent neural network and decoder is also a recurrent neural network. Encoder encodes the source sentence, and decoder uses this encoding of encoder to produce the target sentence one word at a time. So this slide basically shows us how machine translation happens. So I am going home is translated to मैं घर जा रही हूँ here. So as data we will be giving parallel sentence pairs like x1 in source, which is English, and y1 in target. So in encoder what happens is a RNN function is applied over this, and it at any position, let us say ht, it is a function of ht minus 1 and also xt here. So we learned the encoder hidden representations of IN going home in these four states. And when we start decoding, we basically give the last hidden state ht as an input to the first neuron in the hidden layer of decoder. And so मैं घर जा रही हूँ is predicted. So here we see S0 ht. So ht is fed here, which is H0. And at any position, st is a function of st minus 1. So st here will be a function of st minus 1. And also e of y dash t minus 1. So here e means a word embedding. So Nikhil has already talked about it. So what word embedding is. And so for Rahi, we will feed it like 01000 or Generally, word embedding is a fixed length vector of size, let us say 512. We will not talk about it more. And at the output layer, a softmax function is applied, as I described a few slides earlier, to convert these values into a probability distribution. As the parameters of the network, we have U decode, which is U for decoder, V, then W decoder, U encoder, P, etc. And here we see that cross entropy loss function is applied. And the algorithm which is used is gradient descent with backpropagation, which is basically backpropagation through time. So this is one type of encoder decoder model where the state HT of the encoder is fed only as an input to S0 of the decoder. And in another type of encoder decoder model, let us say model 2 here, instead of feeding HT of encoder to only S0, we will feed HT at each time step. So we can see that HT is these dotted lines go to this S0, S1, S2, S3, and so on. And at the decoder, each state ST is a function of ST minus 1, and instead of feeding only embedding of the word produced at T minus 1, we concatenate with HT from the encoder. The rest is same here from the previous slide, so I am not going over it. So this slide describes what problems we face in the encoder decoder model which I described. So I talked about it a bit last time also. The problem is that the model needs to cram all necessary information of input sentence into a fixed length vector. So this is basically HT, which I talked about just now. Howsoever big the input sentences are, all of its information have to be crammed into HT for the decoder to decode. And as the input sentences become longer, the information gets lost. So to deal with this, attention mechanism has been introduced, and attention is used very widely now in many forms in machine translation, like self-attention, etc. We will be talking about it. And at each decoding step, the model learns which input word it must put for more focus on. We will talk about, we will see attention, how it works in the next slide. So attention allows a model to automatically soft search for parts of a source sentence that are relevant to predicting a target word. And the fixed length context vector HT is not used here. So let us see attention in more detail now. So this is basically the same architecture which we saw in the past slides, but we see that between encoder and decoder, box is introduced, which is basically the attention mechanism. So what happens is that when we are predicting the word home here from मैं घर जा रहा हूँ, so for predicting home, the most important word in the source sentence will be ghar. May, raha, and who, all these are not so important. For predicting, let us say the word I, the most important word in the source sentence will be may. So we are basically trying to capture this, that when we are predicting each target word, we are taking a weighted sum over all the hidden representation of the source words. So for predicting home, we will be taking a sum of this hidden encoder representation by multiplying with values alpha 1 1 1 2 2 3 2 4 2 and so on, and the most weightage will be given to ghar here because ghar is most relevant. We try to capture this intuition in the form of equations here. So the encoder equations remain the same. HT is still a function of xt and ht minus 1, and as we still feed HT to S0, like HT will be fed to S0 here. But what happens in the decoder is that we first take some values called EJT from which we get alpha JTs. So EJT is basically a function of HJ and ST. So this basically means that this box with the plus sign is a function of the inputs the hidden representation HS, and also from this dotted line we get ST here, and a tan H function is applied here to introduce non-linearity, and V attention is applied for transforming the, what should I say, transforming the vector dimensions to appropriate way. And after we get this PJTs, we apply the softmax function here again to get a probability distribution over these EJT values. So each alpha at each time step with a value between 0 and 1, and the sum of all the alphas will be 1. And we calculate a context vector here called CT, which is a sum of the alphas and the hidden encoder representations. For each time step, we feed to the RNN decoders this CT value. So we see that ST of the decoder is a function of ST minus 1, the embedding of YT minus 1, and CT here. So this CT basically represent the attention mechanism that at each time step we are feeding the weighted sum of the hidden representations of encoder to decoder, and that it does not have to remember everything at a time when we are feeding S0 equal to HT. This is what the attention mechanism is, and rest remains the same, mostly the parameters. So for the parameters, U encode, U attention and V attention are introduced, and the loss is cross entropy loss. The algorithm backpropagation through time remains same here again. And let us move on. So just wanted to confirm, am I still audible?
Yes, Akash, you are audible.
And any questions till this point? You have presented a number of slides.
Akash, please keep the mic close.
Okay, is it better now, Nikhil?
Yeah, yes, it is better.
Was I not properly audible throughout?
No, it was okay. Just it is better now.
Okay. So moving on, we see different types of attention mechanism here. I presented this slide last time also. So in the left, we see global attention model, which I described just now, where the context vector CT is a function of all of the hidden states of the encoder, H0 to let us say HT. It is called global attention model. And in the right, we see local attention model, where the context vector CT is function of only a few hidden states. Here it is taken as 3, not of all of them. Because in longer sentences, often we don't need to see what each and every word is. Like when we are predicting the 10th word, we don't want to know what is the first word or 21st word, like that. That is not very relevant. And moving on, now I will present some slides on transformer model. The transformer model is has been introduced in 2015 in a paper presented at NIPS by Vashwani from Google. And it is the state-of-the-art model now, which gives the best performance for machine translation. It is widely used. And another model called BERT, which is a language model, is inspired from transformer, and it is also very widely used, but it is not relevant to us. So let me describe transformer model a bit. So one constraint of IRNN models is that they are inherent sequential nature. So like when we are taking a very long sentences as input, we have to go over the recurrent connections one word at a time, and it takes a bit of a time and does not allow parallel processing here. So transformer does away completely with these recurrent connections and uses only attention to learn the global dependencies between input and output. So the transformer allows for significantly more parallelization, and hence is trained faster than IRN models. And it also gives much better results compared to IRN models in a shorter time. That is why it is very popular now. An attention mechanism called self-attention is used here, which relates different positions of the single sequence in order to compute a representation of the sequence. This basically means what we have seen till now in those attention mechanisms. When we are predicting a target word, we were taking attention over the source words. So like for predicting words in English, we were taking attention over Hindi. But in self-attention, the attention mechanism works only on a single sequence. Like to when we are going over a word in a sentence, we will be considering how it is related to the words in that sentence only in the same language. I will describe more about it in the coming slides. This is the architecture of the transformer model. It is a like a big architecture. So let me describe it here. So as input, we basically give the words as input of source language. So they are given as input embedding. So this is the word embeddings. And another thing which it adds is positional encoding here. So positional encoding is added because a lot of parallel processing takes place in transformer, and to tell the model how each word is ordered in the sentence, this positional encoding is introduced. And each encoder layer, like n into basically means how many attention layers we are using, is a combination of a multi-head attention layer and a feed-forward layer. So this encoder is basically like we will have n such boxes stacked on top of each other, and no recurrent connection exists. So we will see this what is multi-head attention in the coming slides, and feed-forward network we have already seen. And coming to the decoder, it introduces another masked multi-head attention here. So we in the decoder also we give output embeddings and this positional encoding. So these are basically output words and positional encoding. But the important thing here is masked multi-head attention is used. So what masking means is, let us say in when we are predicting the fourth word in the target sentence while training, we don't want model to see what the future words are. Like in a 10-word sentence, when we are predicting fourth word, we don't want the model to see what the fifth, sixth, seventh, eighth, ninth, and 10th words are. This is because if we allow the model to see it, then in the future it can very easily predict those words, and the model will not be trained properly. So to do that, the words in the future are just masked out. They are given a value minus infinity so that they are not considered. And in the top we have multi-rate attention feed-forward networks, and we see a linear layer here, which is basically a layer which will convert this output from the decoder to the vector of size target vocabulary. Then softmax is applied, and this connections which we see here, like going from bottom to add and norm, bottom to add and norm, these are residual connections. And residual connections basically, like we can see what it does after it computes. After it is given as input to multi-head attention, it produces an output, and this same input is given as input here. So like these connections were introduced in the context of convolutional neural networks a few years back, and since then it has caught on. Like it gives an improving performance. You can check them out, like residual networks, what is done in Google. And add and norm is basically like adding these inputs and outputs and normalizing them. So normalizing basically means it divides them so that all the outputs are within a certain range. This also helps the model. And so let us see what is self-attention, because it is very important. So we see that as the same sentence is produced, like animal, like the animal did not cross the street because it was too tired. A human being can like catch that this it means the animal. So the animal did not cross the street because the animal was too tired. So animal becomes it. But a neural network does not know it naturally. It has to learn. And the self-attention mechanism basically allows the model to learn these things. So here we see in the fifth layer of the encoder, the animal did not cross the street because it was too tired. For the word it, the most weight is given to the two words, the and animal, which have like in darker orange color, and all of the others in lighter colors. So like self-attention model processes each word and allows it to look up at other positions for clues that can help lead to a better encoding. So the clue for the word it is the words the and animal, and self-attention basically allows it. You can check out more about self-attention and transformer in the paper and a blog by Jai Alamar, which is given as reference here. It describes in much more detail, which I cannot do here due to time constraints. And the self-attention, which is also called state dot product attention, is described here. So to use it, a vector of q, k, and v is used. So this q is query, k is key, and v is value. The query and key are used to calculate weights, and then a weighted combination of these values are taken. So we see that we fit q and k to a matmul, which is like matrix multiplication. We then scale it using this dk. And this mask optional is for the mask multi-head attention, which is the first network in the decoder part. It is optional because it is not used in encoder. And then a softmax function is applied for to convert it into a probability distribution. And the weighted sum of these v values is taken here. So this query and key values give rise to a probability distribution, which is multiplied over v, and we get the output here. So self-attention is implemented like this in the paper for query, key, and v values. And a concept called multi-head attention is used in the paper also. So what this does is basically, let me describe it in the diagram. It is better described. So it takes this v, k, and q value, key, and query pairs and breaks it up into a number of like parallel layers. So basically matrices like wv1, wv2, wv3, like these matrices are multiplied with v to break it up into like h parallel layers. Here the value of h is taken as 8. And after this, the scale dot product attention is applied, which I described in the previous slide. These parallel layers are concatenated into a single vector, and the linear layer is applied. So linear layer basically transforms the vectors. So basically, it again transfers these v, k, and q values to this same input dimension. And this equation basically describes that multi-head basically is a like w0 into concatenation of all these head, and each head is a scale dot product attention like q w1 q, like this i's will be from w1 w2 w3 wq1 wq2 to wq8. For similarly for wk and wv, this will break u, k, and v into 8 parallel vectors or matrices, and each of the matrix will go through attention layer to produce head. So head 1 to head 8, the vectors will be concatenated and passed to the linear layer for w0 to give back the multi-head value. So I tried to describe transformer here, but it is a very like big model, and you can check out more in the how it works in the paper or the blog by Jai Alamar. I have given it in the reference at the end of the slides. So this slide is on subword and empty. I talked about it a bit in on 8th also. So subword segmentation basically breaks up a word into its parts. So for example, for morpheme segmentation, the unhappiness will be broken up into 3 morphemes: unhappy and ness. So like this is what happens in subword and empty. It is also sometimes the pre-processing step in NMT systems. So like as I said, compound words with morphological variation are very common and they can be broken up. So let us move on. So byte pair encoding algorithm is also for subword encoding only. It breaks up each word into its subparts. Like I described the algorithm, it is a compression algorithm, and it basically takes the frequencies of two tokens side by side, like AA, AA, AB, DA, and the most frequent tokens are replaced by a bigger token like AA becomes Z. Then the most frequent token is AB here. AB will become Y, and so on. And like this, byte pair encoding algorithm works, and Roger Federer becomes Roger Federer, like solar system becomes Sone system. Like this, byte pair encoding helps, or subwording helps rather. And this slide is on pivoting. So pivoting basically means when we are trying to translate from source to target, we go through a pivot language. So for English to, let us say we are trying to translate to Marathi, we will go through the language Hindi here. And some problems with basic pivoting is that when we are going to two models, the decoding time doubles, and also the error gets propagated as we are going translating through two models instead of one. We see some basic pivoting models here, like for Italian to Romanian, English is used as a pivot. So it will go from Italian to English, then English to Romanian, and so on. And in the right, we see pivot-based transfer learning, which like basically pretends the source to pivot and pivot to target models, then copies the parameters of source encoder, target decoder here, and we get the final model. We have some source to target parallel corpora. We can use it to fine tune the model. Fine tune basically means we will train the model for some time using that parallel corpora. And this slide is an empty evaluation. So earlier manual evaluation was used with the parameters of adequacy and fluency. So adequacy is a parameter which basically means how faithfully the meaning of a sentence is transferred. This means that whether when we read the target sentence, we are getting the meaning of the source sentence by reading the target sentence. The words may be a bit misarranged or not translated exactly properly, but we still get the meaning of the sentence after translation. And fluency basically means how much is it acceptable to the native speaker. So here the order of the words needs to be absolutely perfect. The inflectional forms of the words need to be perfect for a sentence to be fluent. So we see a small example here, like मुझे भूख लग रही है is more fluent than मैं भूखा महसूस कर रहा हूँ. This sort of मैं भूखा महसूस कर रहा हूँ is not required. We can say it more fluently using मुझे भूख लग रहा है. But problem with manual evaluation is that a human being takes a lot of time to evaluate the performance of the empty systems, and we do not have so much time. So to deal with this, automatic evaluation matrices have been introduced, which are like word based or edit distance based, etc. Some of the well-known evaluation matrices are Blue, then Perplexity, Meteor, etc. And this slide talks about Blue. So Blue basically means bilingual evaluation understudy is the full form. And we see the equation of Blue here. So BP is a brevity penalty, and brevity penalty is used to penalize the model based on length of generated sentence. So if the source sentence is of length 15 and target sentence is of length 3 or 4 words, then brevity penalty will penalize this blue value, and blue score will be lower. And the brevity penalty is multiplied with exponential of Wn into log Pn. So Wn is basically a weight, And this basically means the weighted sum of the log of PNs. So PN is basically, PN means the perplexity. The N means the n-gram perplexity. So like it is a weighted sum of P1, P2, P3, P4, which is unigram perplexity, bigram perplexity, trigram perplexity, and so on. And the blue score is a measure of how good our translation system is performing, and the higher the blue score, the better. So what perplexity exactly is, I will describe in the next slide. And sorry, the PN basically means precision here, not perplexity. I'm very sorry. So precision basically means the percentage of results we get which are relevant. So to compute precision of a sentence, we have to count the number of candidate translation words which occurs in any reference translation and divide by the total number of words. So here the candidate translation which we get is वो एक चित्रकार है and reference is वो एक चित्रकार है. So in the denominator we will have the length of candidate sentence which is 6, and in the numerator we will have the number of candidate words which also appear in the reference. So like wo appears, ek appears, chitrakar also appears, he also appears. So the 1 gram precision here will be 1, which is like 6 by 6, but we will get high blue scores here, but that is not correct. This is because we get 3 times chitrakar here, but we should get it only 1 time. To deal with this, a modified form of precision is used. So what happens here is that the denominator remains the same, which is length of 6, and for the numerator we will see how many times we can have chitrakar. So even if chitrakar occurs 3 times in our candidate sentence, in the reference we only have it 1 time. So like wo will contribute 1, ek will contribute 1, he will contribute 1, so it will be 1 plus 1 plus 1 3. But the chitrakar, all these 3 will contribute only 1 and not 3 like last time. So the modified precision score will be 4 by 6 here. So this like this describes what precision is. You can check it out in more detail in the blue paper itself. And these are some experimental results which we have from our lab. So for the using only transformer, we get a blue score of 26. And for fresh table injection, we slightly improve from the baseline. From 26.08, we go to 26.4, an improvement of 0.32. For language agnostic training, we improve from 26.08 to 27.97. Like we get an improvement of 1.89, and for marking segmentation we improve from 1.97, from 26.08 to 28.05. These blue scores are for English to Marathi translation, and at present I am trying to improve the performance of English to Marathi translation in many ways. These are summary of some ways and the corresponding blue scores. And yeah, this is a reference slide which has a reference for what I presented today. And that is it from my side. Thank you. Any questions from the audience? Raj, are you there?
Yes, yes. I think there are no more questions from the audience. Thank you, Akash, for the wonderful insight about the neural machine translation, the evolution of neural machine translation, and how we can evaluate the translation. So I will take it over now.
Yes. Thank you, everyone. And I have stopped sharing. Raj.
Yes. I will start the my session in a while. Let me just talk to someone and I will get back to you in 2 minutes. Hello everyone. Is my screen visible?
Yes,
Yes.
sir.
Okay. So once again, I welcome you all to this demo session for machine translation. My name is Raj Prajapati. I am an MTech student, currently working under Professor Prasenjit Majumder in DAIICT. So I will be giving a short demo of machine translation. Yeah. So first of all, as I think already explained, so we'll be basically implementing a sequence-to-sequence model. So basically, what is it is? So we'll have an input sequence going through a model, and we will have the output sequence. So for each sequence of input, we will have some output token or output sequence. So the image is taken from Analytics Vidya. So basically, this is if we go deeper into this framework, what is a sequence model, we have is an encoder and a decoder. So encoder encodes the source language and give a latent representation. So latent representation is nothing but an intermediate form of representation of the data, which is used by or it is taken as an input by the decoder, and it takes the target language into account and produce some output for us. So if we see this example, this is German to English. So if we input ist as hype, we will get it is hot as an output, which is in English. So what is the system architecture we will follow? So first of all, we will have the input. Input is nothing but German sentences. We will build some embeddings, which can be Keras embedding or word to vec or glow. So embeddings are nothing but a way of representation of data, because the text data is not directly processable by our system. So we always have to convert our textual data to numbers, and so just it is done by embeddings there. And then we will pass those representations to encoder. The encoder will make later representation, and which will be fed to decoder. And then at the end we will have a dense layer. So dense layer is nothing but a layer which will basically predict the probabilities for the target vocabulary. So since we have to predict words, so we have to somehow figure out which word actually we want to predict at one point of time. So which is done by dense layer, and then if we will combine all the individual inputs to have our output sentence. So I think that's much of a theory from my end. Let's jump towards the code section. Yeah, so this is one collab notebook that I have prepared for this session. I will share this notebook after the end of my session, and after 6 p.m. onwards, you guys will be doing an hands-on session. So you guys will be using this reference code to build your own empty system. So data source I have used is from this website. So this small website contains some of the data for language pairs like English to German, English to French, French to German, etc., etc. So we are basically using 50,000 parallel sentences to carry out our task. So this is a Spanish English translation system using LSTM. So LSTM is long short-term memory and improved version of RNN. So first of all, we'll import the necessary libraries. So this is NumPy, Pandas, Keras. So this all you can read afterwards. So basically, this is the small models that we are going to use. So sequential is nothing but a model. We define a model as a sequential model. Dense is the layer, LSTM is the layer, embedding is the layer. Tokenizer, I will explain in a while. And similarly, we have other tools. So, because Python has most of the things inbuilt, so we have to just pick and choose some of the things and use it to customize our product. So basically, we'll be using this data set that I recovered from the website. So this data set contains these parallel sentences, which is separated by tab. So as you can see, there are English on the left side and Spanish on the other side. So these are the parallel sentences that most of the things we talk about. If we start, it starts from the single words to more bigger sentences. So let's take this sentence. So Tom becomes nervous whenever he has to speak in public. So which is, and its translation is Tom se pone nervioso cada vez. So this is a Spanish equivalent for this particular sentence. So we'll use these kinds of sentences to train our LSTM based model. So this is a text file. We will first of all import the text file, and then we will read all the content. Since it is like all these sentences are separated by individual sentences are separated by like enter or /n pointer, we will first of all split all the whole text in forms of sentences, and then individual each sentence will be splitted by the tab space, because for a particular sentence we have English and Spanish counterparts, so we have to separate them out in order to individually process it. So we'll first split it by tab space, and then we'll take only the first 50,000 data sets. This is just for demonstration. In general or in real, in practical, we often take a lot of data, not just 50,000. We take around whatever the data we have available on internet or from some of the recognized sources. We scrape all this data, because if we simply talk about machine learning or deep learning models, the more data you feed, the more better the model can train and the better results we can get. So this is just for demonstration. We are using 50,000. And then we will do some cleaning. So data cleaning is one of the essential parts of NLP system. So we will first of all clean all the extra symbols, because these extra symbols, for a small network, it can wrongly train, or it can actually corrupt the whole model. So we will remove these symbols from the data. We'll replace it by a space, so it won't bother us anymore. We will do it for both the sides. Since Spanish is also English, the script of Spanish is also in English, so we can directly remove the punctuations or the symbols. But if we are trying to use some, if we are dealing with some other languages, let's say Hindi script or Gujarati script, this pre-processing or cleaning step varies from language to language, because some of the characters which are represented internally can be can fall into this category. So we have to be very cautious about that. We don't actually, because it happens that if you are trying to clean a Hindi dataset and you accidentally remove all the matras from the particular text, so that is something that we have to avoid. Other than that, we have to transform the data, since both the sides are in English script. So we have to lowercase all the, so either you can do the lowercase, or you can convert every letter into uppercase. So this is basically a good practice to avoid the sensitivity. Or so basically when you have to build a vocabulary. So your machine translation system needs to know what all words I know in terms and what all words should I predict. So basically if you have to build a set of words. So for building the set of words, if we don't keep all the words on the same platform, then it might happen that we say Taj Mahal with T capital as a unique element, and Taj Mahal with lowercase t as a unique element. So, but indirectly they are both same. They are referring to the same thing. But since because of the case issue, we are dealing with as individual. That is something we have to avoid. And then moving forward, we are using tokenizer. So tokenizer will basically tokenize. So it will basically go through all the text and pick each and every word and process it so that it basically keeps a count of what all words I have and what is the count of that word and how I can use those information to better train or help our model train. So we'll fit all the data individually. So we'll have two tokenizers because we have two languages. So we'll have English side tokenizer and we will have Spanish tokenizer. Individually, it will read all the text, and that's why we have to differentiate, or we have to segregate the data so that we can train these tokenizers and other parts individually. So and then after we build the vocabulary, we'll have some rough count of how many words we have in this particular text. So in this example, we have around 6,000 text, so 6,000 tokens or 6,000 words in our English and 14,000 on our Spanish counterpart. So then after that, since we have 50,000, roughly 50,000 data, we have to first split the data into training and testing sets. So why this is because we often, if we train our model, we have to somehow test it and check how much accurate the data is, or sorry, how much accurate the model is. So we will use this train test split to split the document into 80-20 ratio. And we have the training and testing set. And then after that, we will basically, the point I talked about is we can't actually process textual information. We have to somehow convert it to numbers. So we have to like encode all this token or individual words into a number so that we can somehow make a represent, or we can represent in a latent space. So we will use this text to sequences function of the tokenizer. So we'll take the tokenizer, the length and the lines. So length is nothing but, sorry, I forgot to mention one point. So whenever you are dealing with an LSTM based or an RNN based model, you have to first deep dive into the data and see what is how spread out or how diverse is the data. So as I show you in the, as I've shown you, we have sentences which contains around 8 to 10 tokens. Also, we have sentences which contains only one token. So in that case, we have to set up like a rough idea, or we have to set some length of the vector. So we'll basically keep the maximum maximum tokens in a sentence as our threshold, or basically the way of representation. So basically we will keep 8 as our English length. So whatever the text we have, whatever the sentence we have, we will always have a representation of 8 in our system. So the sentence having 1 token or sentence having 8 token will be having the same length. But so that's why, so this will give us the tokenized, this line will give us the numbers for each line, for each sentence, and then we will pad all the, so let's, so if I give an example, so let's say I have a word which is, let's say India is great. And I have another sentence which is India is a great nation and prosper. Let's say this is just an example. So for this particular sentence, whatever the text to sequence we convert will only be having a vector of around of 3 elements. So let's say 2, 2, 2. So this is just a representation, and for this particular case, we will be having a vector of around 6 numbers. So it will be having something like this. So to make this equal, or to make it on a common ground, we use this length and we pad zeros at the end. So if you pad zeros at the end, what we'll have is, we can see now we have bring all the sentences onto the same ground. So similarly, we will split the data into like X and Y. So X and Y is nothing but your English and your input is your training X part, which is Spanish, and training Y part is nothing but your Y. So what we do is we give English and its Spanish equivalent part into the model. So while training, and so model basically trains, okay, So for this particular sentence or for this particular tokens in English, we will be basically training, we will be getting this Spanish counterpart. So that similarly for test set also, but for test Y, this test Y will only use when we are trying to check how efficient the model was. And now we will define the model. So first of all, we will use the sequential function. So we'll initialize the model. We'll add an embedding layer. So embedding layer, as I already mentioned, you can, if you have the provision of word2vec or glove embeddings, you can directly use that embeddings as well. But for this case, we are only using this Keras embedding layer. We are representing, we are getting a representation of around 256 from whatever the Spanish vocab we have. Then we have the LSTM encoder layer, which is around 256. So LSTM is simply an RNN. So we are using 256 layers of the LSTM in the encoder part. Then we have the repeat vector. So repeat vector is nothing but if you want to connect two LSTM individual layers, we use the repeat vector as a middle point. So we have the repeat vector, which is kind of containing the latent representation. And then we have the next LSTM layer, which is nothing but the decoder phase. So this very thing is encoder, and this very thing is decoder. And then at the end, we have the dense layer. So dense layer is nothing but having the probabilities for each of the target vocabulary words. So we have the softmax activation. Softmax activation is already explained by Akash sir. So softmax basically normalizes all the individual probabilities between 0 to 1, and whatever the highest probability we get for a particular word, we take that word. And then if we summarize the model, we have the embedding, we have the LSTM, we have the repeat vector, we have the LSTM, which is decoder, and then we have at the end we have the dense layer. So if we will compile this model using IDEM optimizer and sparse categorical cross entropy. So it's a very fun combination that if you are using softmax as the activation function, then we'll always use sparse categorical cross entropy as the loss function. So this is a standard practice. So whenever you are using softmax, you will always blindly use sparse categorical cross entropy. And optimizer we can vary. We can use SGD, we can use AdaGrad, or there are a lot of other optimizers available. And then we can start the training phase. So we can save checkpoints at some interval so that we don't lose the best model while training itself. So this is how we can save the model or the checkpoint. And then at the end, we'll go through the fit function. So fit function basically is the starting point of your training. So we give the input data, we give the output data, we give the number of epochs. So epochs is nothing but how many times you want the model to go through the data. So if we are saying 30 epochs, so the model will go through each of the 50,000 sentences 30 times. And so in order to learn the how we can predict the English data for a particular Spanish part. And the batch size is 100. So batch size is nothing but whenever you are training, batch size helps us to reduce the model size. So if we don't use batch size, then the whole 50,000 data will be loaded at once. So, and it might exhaust some of your RAMs of your PC. So we deal with batches. So batch size, so at a time we only take 100 data points, and then after completion of that 100, we take the next batch. Validation split. So validation split is one of the main thing while training. So validation split is nothing but we train the model, and during the training phase, we actually check how is the training direction good or not. So for that particular purpose, we use validation data. So we take around 20% of the training data as validation data. So basically it checks if the model is training good or not. And it is a metric to check if the model is overfit or not. And then we will train the model for 30 epochs. So as first epoch, we have a loss of around, we have a validation loss of around 3.54. And then as we go down, or as we go towards the epochs, one after the other, we gradually lose the validation loss, which is good, because we always, in machine learning or deep learning models, we always try to minimize the loss. And that is the main goal of training a deep learning model. So we always try to minimize the loss, and whatever the least loss we get, we take that particular instant or model. So similarly, if we go towards the very last epoch, we have we can see we have around validation loss of around 1.83, 1.85. So and 1.82 here as well. So we can take the best, we can say the best model, and we can only use that model for evaluation. So if we don't want to go through all the statistics, what we can do is we can plot the results of the loss. So this is on the x-axis we have the loss. Sorry, not this one. We have on the x-axis we have the number of epochs, and on the x-axis, y-axis we have the loss. So we can see that both are curves. So blue is the training loss, and orange is the validation loss. So we can see that after this point, the validation loss becomes stable, and if we go towards more like 40 epochs or 50 epochs, this will gradually increase. So whenever the orange line starts to increase again, it means that the model is getting overfit and on the training data, and it is not getting enough diverse data to work on. So we generally avoid that particular thing, because if we try to overfit the model, then while testing it will give very bad results. And then we will save the model. We have saved the model as ENES model in your drive. This is a Colab notebook, so you can save at current runtime as well. And then we will basically use the model.predict for each of the test data. So this model.predict will give the softmax highest, the index of the highest words at a point of time. So we will take the argmax. So argmax basically returns the where index at which the highest probability has achieved. So we will get a 10 cross 10 or whatever the 8 cross 8 matrix, the length of the text sentence that we have defined earlier. And then we have to decode that particular, because we are dealing with numbers. So we will get some numbers at this point of time. So then we will get the individual words. So this code is very straightforward. You can simply decode it. So basically we are getting the word at using this function here, and we will check if the word we have got is 0 or not. So basically we sometimes we get some spaces in between, so we can avoid that spaces, and we can only save the legit tokens in the output sentence. So then we will join all the words that we have, because it is a sequence, or it is like LSTM models are predict one word at a time. So we have to take all the individual words, and then we have to combine that word, all the words, to get the final string, output string. And then after training, we can I have saved this in a data frame. So this is how our data is. So the actual output for some of the translations was Tom will play for this, and what we predicted was Tom let go, follow, taste this. So since this model is a miniature model, so it might not be very good at prediction, but it will somehow give some of the good, let's say in this example, let's play volleyball. So here we have let's play, but then we have somehow messed it up. So we are in a good direction, but it requires some more training and some more data. It will gradually better. So at last we have to check how accurate the model was. So we can simply use the blue score for calculating the model accuracy. So we have around 28 blue score, which is not so good in terms of Spanish English, because Spanish English, a lot of work has been done in this particular phase. But if I see in a miniature model, in a miniature setup, this 28 blue score is quite good. So that is how or 30 minutes to run, given that you have the data files available at your end. So this is a very small demonstration by me, and if you have any questions, you can ask, because after 6 p.m. You all have to work on this particular notebook only. So thank you, and I'm open to questions on this particular notebook and the previous slides as well.
Hello, sir.
Yes.
Sir, what is our assignment?
It is an hands-on session. So sorry, I forgot to tell you about that. So it is not to be done now only, because I think Pushpak sir will take a session in 10 minutes. So basically your task is to pick a language pair, pick any language pair, not the one that I have shown here. Take any language pair, let's say English, German. I have pasted I will share this notebook. So you have this particular data source link, so you can take data from here as well. So you have to pick a language player, download and prepare the data, understand what the data is, model an empty system, and report the best blue score. And you can additionally, you can also figure out what extension and you can do to upgrade this blue score. Let's say you are getting a blue score of 20 and you want to somehow boost it to 25, 30. So what all things you can do, that you have to figure out, and what all on what aspects the model is lagging. Let's say in linguistic, in getting the more linguistic knowledge, it is lacking. So these kinds of reasons are more welcome. So at the end, I will open one assignment in the classroom, and you can submit it. I think by tomorrow night or maybe day after tomorrow. So that's it for today. So after 6 p.m. we will be getting. So I will be available, and you can ask me questions on if you are getting an error or want to do something and you are not able to do it. So that is open. I'm open for that. So other than that, is that answer your question?
Yes, sir. So this English German data file is available at that time?
Yeah, I will post this particular notebook on Google Classroom, so you can use the link that I have shown just now. They have many language pairs data available, freely available, so you can download it and use the reference code as well.
Okay, sir. Thank you, sir.
Jenny Raval. Yes, from my end, I don't have much to share in my slides, but yeah, you will get the slides after the evening or so. Yeah. So anyone else have any questions to ask? Okay, so we have Aditya from IIT Bombay. Aditya would like to say something till Pushpak sir joins the session. Okay, so we will have a short break of 5-10 minutes till Pushpak sir arrives, and then Pushpak sir will continue the session. So stay online. Pushpak sir can arrive at any point of time.
Hello.
Hello, sir. Good evening.
Hello.
Yeah, good afternoon. Good afternoon. So I think you'll have to give me presentation, right?
Yes, sir. Yes, sir. I'm giving you.
Hmm.
Yes, sir. You are co-host, so you can directly start presentation.
But I cannot see the screen. It is saying meeting topic and so on. Oh, share screen, shall I say? So
Yes,
is
sir.
my screen
Yes,
visible?
sir. Yes, sir. It is visible.
It says cooperative neural MT.
Yes, sir.
Okay. Okay. So good evening to everybody. So in the last part, this is part 2. In the last part, what we did was that we looked at this pan-Indian machine translation experience, and this was an experience of working with 7 Indo-Aryan languages, okay, and 3 Dravidian languages. So what happened was that we found that distinctly the Indo-Aryan group showed higher level of blue score, okay, and the Dravidian languages had much less blue score, and that happened mainly because there was a lot of agglutination in the language. The long words are formed by stacking together small morphemes. So then we tried to ameliorate this problem, improve the accuracy by making use of subwords. Now, subwords are characters, morphemes, syllables, orthographic syllables, and byte pair encoding. Now, there is an interesting approach which was considered by us for orthographic syllables. So orthographic syllables are syllables which end in a vowel. See, if I have jaunga, then we form a syllable which finishes with a vowel. We go on observing characters until we meet a consonant. So jaung, it goes up to jaung, and then unga. Okay. So this is done so that the ambiguity of syllabification is avoided, because the syllable boundaries also can be ambiguous. And the byte pair encoding, of course, is based on statistically significant patterns. Lecture going on. कल करेंगे. Just 1 minute.
श्रीपर्णा मैडम का फोन आया था और उन्होंने बोला कि आप ना एक दिन आएंगे को मेल डाल दीजिए रिक्वेस्ट में प्रोजेक्ट ट्रांसफर का तो फिर हो जाएगी शायद आपको मैसेज भी किया.
Okay, so this is byte pair encoding is statistically frequent patterns. So when we do this byte pair encoding and other subword based statistical machine translation, we find that the blue score improves definitely at all places. So morphological segmentation on the strings improves the accuracy sometimes by more than 20%, as we see in case of Punjabi Malayalam. Okay. So this was discussed in the last meeting, last lecture, which is part 1 of machine translation. And byte pair encoding achieved much higher level of accuracy, so about 35% higher level for Punjabi and Malayalam. Now, we found that there was this improvement in all families, within families and across families. So for all, the byte pair encoding based machine translation really scored over others, morphological segmentation based and orthographical syllable based. Everywhere this red bar is for byte pair encoding based machine translation. So byte pair encoding is now the de facto subwording standard for neural machine translation. For statistical also, we found it to be effective. Now, we used these ideas and then proceeded to assisted neural machine translation. So the main idea was that how can languages help each other in doing neural machine translation? That means how can you have a neural network which is trained on one pair of languages and used for a completely different pair. So that is called zero-shot machine translation. Or you do not change both the languages, you change only one language, and then also can you use the same network, same architecture for machine translation. So this uses what is called cross-lingual embedding. Now, cross-lingual embedding is a very attractive idea, and since multilingual natural language processing is extremely hot these days, they're receiving a lot of attention. That means, do you do anything, any NLP task, machine translation, question answering, sentiment, anything. If you have done any, if you have built any system for language L1, it should be possible to use that system for other languages also. Okay, so that is the intuition and that is the demand from cross-lingual neural NLP. So the cornerstone of this kind of work is cross-lingual embedding. By the way, is my slide visible? Created through 3 approaches, it says.
Yes, sir.
Okay. So cross-lingual embeddings are embeddings of words independent of the language. So if cat is the word in English and Billi is the word in Hindi, Vedal is the word in Bengali, all of them, because they mean the same thing, all of them should have the same embedding. Okay, this is the desire for cross-lingual embedding. So these cross-lingual embeddings are created through 3 approaches. Simple word translation, that is making use of bilingual dictionary, from parallel corpus, and from monolingual corpus, which is completely unsupervised. Okay, so you can have these 3 approaches: bilingual dictionary based, parallel corpus based, and monolingual corpus based, which is completely unsupervised. So let's look at the foundational intuition. So these cross-lingual embeddings exploit what is called the idea of isometricity. So isometricity, we can come to the formal definition after looking at this picture. Isometricity refers to bringing embeddings in the same space. And this again is motivated by an interesting observation. The observation is this, that when we take the words of a language and create their embeddings, we find that words with similar properties are hanging together. So banana, so pear, apple, banana, these are fruit words. Okay, cow, dog, cat, these are animal words. Moo, bark, mew, these are calls of animals. So we see that the embeddings of words having similar property, similar semantic property, are close to each other in the geometric space. And this happens independent of the language. Okay, we see the same thing happening in Basque language, where we find that these animal words, katu, bel, zakur, and so on, they are together. So words with similar semantic property tend to form clusters independent of language. Okay, so this is a very interesting observation, and this is called the isometricity property. Of course, this has been questioned by data scientists who observe the behavior of embedding space. They have found exceptions also, but in many cases this property holds. So as a result, we think that it is possible to find out two matrices Wx and Wz, such that if we multiply the word embeddings X of language L1 and word embeddings Z of language L2, then they come to the same cluster in the shared space. So the picture then emerges as follows. Pear, apple, banana, udare, sagar, zagar, I think. So udare, zagar, banana, these are Basque language fruit words. Okay. House and etxe, they mean the same thing, they are together. So these embeddings are together, even though they come from different languages. So cow, behi, katu, cat, sakur, dog, these are animal words from English and Basque. They again hang together. So we have been able to map the word embeddings of Basque and English into the same space by multiplying them by appropriate weight matrices. So now the key question, of course, is how do you find those weight matrices? So that's found out by starting from monolingual embeddings. Okay. So I illustrate this with Hindi and English. So we have the Hindi's embeddings, Billi, Mez, Seb, computer, kursi. So these are typically 300 dimension word embeddings. In English also you have cat, apple, table, chair, and computer, again 300 dimension word embeddings. So they are created from English monolingual corpora and Hindi monolingual corpora. Now we do a common cross-lingual space population by multiplying X with WX and Y with WY. So this learn WX and WY, the transformation matrices. D is the dictionary mapping between L1 and L2 vocabulary. DIJ is 1 if the ith word of L1 belongs to jth word of L2 or maps to jth word of L2. So using these cross-lingual embedding ideas, we investigated the machine translation amongst different languages in completely unsupervised setting. So neural machine translation uses huge end-to-end neural network. Generally, it has two components, the encoder and the decoder. So by now, through my lecture and through lectures of Akash, Nikhil, and now demonstration of Raj, you probably know that it is encoder-decoder combination, which is the neural machine translation basic architecture. So many books, so little time goes into the encoder-decoder architecture, and out comes the Hindi sentence, बहुत सारी किताबें और बहुत कम समय. Now, this graph we had seen before, that as the data increases, neural machine translation very quickly overtakes in terms of accuracy any other system. So in unsupervised NMT, the architecture consists of one shared encoder and multiple decoders. In the encoder side, fixed cross-lingual embeddings are presented. Denoising, autoencoding, and back translation are the key steps in unsupervised neural machine translation, which I believe you have gone through the lectures of Nikhil and Akash. So back translation and denoising, these are absolutely foundation for neural machine translation. Denoising mainly teaches the neural network, the syntax of the language, and back translation teaches the vocabulary. I mean, this is an overgeneralization and maybe oversimplification, but roughly these are the main functions of denoising and back translation. And you can compute what is called the round trip blue score, where a source language sentence goes through the target language translation, and the target language translation is again taken back to full circle to obtain the source language sentence. Now, if you can measure the distance between the original source language sentence and the sentence obtained by two translations, source to target, target to source back, then it gives you a way of measuring the performance of the unsupervised neural machine translation. So round trip blue score back translation denoising, these have been found to be kind of very fundamental building blocks of neural machine translation. So our approach in this work was joint training of multiple languages. We take n languages without any parallel data. And in this particular case, we had 4 languages: English, French, German, and Spanish. And we found appropriate matrices by which the languages of French, German, and Spanish were mapped into the English space, okay, in completely unsupervised manner. So a German word would map to the English space, similarly French and Spanish. So the geometric structure of words we have already discussed, and we have also observed in for Indian languages, dog, tiger, cat are hanging together. Bag, kutta, billi, they are also together. So this is the isometricity property, and after cross-lingual mapping, the Hindi and English word embeddings come together. Now, the multilingual embedding, as I said, L2, L3, up to Ln, these embedding space is mapped to the L1 embedding space. Now, the fully unsupervised cross-lingual mapping is based on two important papers. One is by Connu, Lempel, and Dinoyer, and Ranzato and Jago, and the other paper is by Artext et al. So both of them create a cross-lingual common space for word embedding. Okay, and the basic steps involve singular value decomposition, by which the dimension is reduced, and there is this generator discriminator architecture, whereby one part of the architecture tries to fool, okay, by producing synthetic sentences and asking if that synthetic sentence can be distinguished from the actual sentence of the language. So this kind of this approach to generation of cross-lingual embeddings between two languages makes use of generator and discriminator both. Okay, and the inspiration is really from computer vision, where the discriminator network is challenged to see if it can distinguish the fake image from the real image. So here also, can we distinguish the synthesized sentence from the actual sentence? So there are these stages of mapping and discriminator. The whole processing is controlled by two loss functions. There is one discriminator loss function, and the other is called the mapping loss function, where the discriminator is supposed to distinguish between artificial and real sentence, and the mapping loss is for obtaining the basic cross-lingual embedding. So cross-lingual embedding generation is a topic by itself, and we'll move on to making use of these in our machine translation task. So we have this shared encoder decoder architecture. So we have to make use of what's called denoising. Suppose the original sentence is, an investment in knowledge pays the best interest. After noising, we get the sentence, investment and in knowledge pays best the interest. So the words have been permuted, and we insist that the correct word order is obtained at the output. So thereby we teach the machine, train the machine, the syntax of the language, okay, by insisting on producing the correct word order. The parameter change happens such that the syntax of the language is absorbed. So we learned, for example, that investment and is not the correct order, and investment is the correct order. So article coming before the noun is a syntactic issue, okay. So article coming before the noun is learned, and we have taught the machine a piece of syntactic knowledge. Where should the article go, before the noun or after the noun? Similarly, for a superlative adjective, the article the should come before the adjective, not after the adjective. So this way, by disturbing the order, we teach the machine the syntax. So from the shared encoder, multiple decoders are trained to produce the target language sentences. So our approach consists of the following. You back translate between L1 and L2, L3, Ln. So L1 is English, L2, L3, L4 are German, Spanish, and French. And then we back translate between English and non-English. So the byproduct of this is that zero-shot translation happens. The network learns to translate between unseen language pairs too. So back translation, what happens is that we have this shared encoder where the L1, if L2 is input, then we obtain L1 star from the decoder side, which is from that decoder, which is for L1. So if it is English, Hindi, maybe I introduce the English sentence and I obtain from the Hindi decoder a noisy and inaccurate Hindi translation. And that Hindi translation L1 star is fed into the shared encoder, and the translation is obtained from the L2 decoder. So this is the L2 star, which is a noisy version of L2. So it may be a wrongly ordered or different vocabulary sentence, which is different from the source language, source and original source sentence. So the difference between L2 star and L2 is used to teach the machine the vocabulary of the two languages. Okay, so this is the idea which has been illustrated by multiple slides here. Now the interesting things are the observations that we made. So news test 2013 and news test 2014 are again standard benchmark data for machine translation. So it has pairs like French, English, Spanish, English, English, French, English, Spanish, German, English, English, German. So keeping English as constant, we have parallel corpora for other languages mapped to English. So on news test 2013 corpus, for French English, we could obtain an improved blue score of 0.66. For Spanish English, the improvement was 1.48. English French 0.43, English Spanish 0.81, German English 0.64, English German 0.85. So we notice that there is not great improvement. There is not great improvement. I mean, 0.66, 0.43. These are not very large improvements, but nonetheless, the improvement is there, and the test of significance by standard means like chi-square or student t-test showed that these increments are significant. Similarly, news test 2014, we did obtain improved blue score, and the improvement was significant. And if we look at the outputs qualitatively, we do see that we are obtaining reasonable systems. So this is the French sentence, which I'm not going to read, but the reference English translation is preparation to manage a class in a North American and Quebec context. So this is a phrase, not a full sentence. The baseline system with the French English available corpus produces the sentence, the build up to manage a class in a Australian. So you can see that the sentence is hardly acceptable. But our system, multilingual, cross-lingual system, produces the preparation to handle a class in a Latin American context. So the reference translation was preparation to manage a class in a North American and Quebec context. What we obtain is the preparation to handle a class. Okay, manage a class has become handle a class. In a Latin American context, the words were North American and Quebec context. So Latin American was introduced by the system, which is a characteristic of neural machine translation, especially unsupervised neural machine translation. A big problem there is name substitution, arbitrary name substitution. The next sentence is, there is going to be a change in how we pay these taxes. Bilingual baseline system, there will be the change in the course of whom we owe these bills. Okay, so taxes have become owing the bills. Our system produced, there will be the change in the way we pay these taxes. So this is almost identical to the reference translation. So this was a paper in ACL 2019. ACL is the topmost conference in natural language processing. So looking back, when at least I think of why the paper was accepted in spite of not huge amount of corpus and so on. Whatever little data we got from public forum and open forum, with that we could produce pretty high quality machine translation. There will be the change in the way we pay these taxes. For German English also, we observed similar phenomena. For this German sentence, au, diese, frage, soll, etc., this question should also provide information regarding the preconditions for the origins of life. Baseline system produced, this question will also ultimately give clues about what there are for the evolution of life. Not bad. Okay, at least the meaning can be deciphered. Our system produced, this question will ultimately give clues to how there is conditions for the emergence of life. So reference said origin, baseline system produced evolution, and our system, multilingual system, used the word emergence, all of which are synonymous in this particular context. The next sentence, he is still accused of passing on secret information without authorization. So this is some kind of spying situation. He is still accused of passing on secret information without authorization. So baseline system, him will continue to be accused of stealing unlawful information. Nearby, but not exactly the meaning intended in the source sentence. We produce, him would continue to be accused of illegally of leaking secret information. So you see the meaning is transferred, but the syntax and choice of words is not very good. Him would, him is accusative or dative form of the pronoun he, but the actual sentence has the nominative form. So case marking has gone wrong, and accused of is there in all the translations. Passing on secret information is becoming leaking secret information, which is okay. And stealing is not really the correct word, because by stealing one can keep the information with oneself. That is not same as passing on. So there the baseline system is below expectation. Spanish English also was interesting. Now Spanish we had observed that Spanish had the largest amount of monolingual corpus. So the larger the monolingual corpus, the better is the pre-trained embedding quality. Because after all, we have to start with pre-trained embedding and go on to the cross-lingual space. Now, in the Spanish, for the Spanish sentence, the reference English sentence is, students meanwhile say the course is one of the most interesting around. Baseline system, the students by their part say the practice is one of the most intriguing. Not really near to the meaning. Our translation is, the students by their part say the course is one of the most interesting. So one of the most interesting is correctly rendered by their part. Okay. By their part comes from both baseline and our system, where there is nothing like this in the reference translation. In Spanish, he does not hesitate to reply that he would never accept a request from an unknown person. This is the translation of the Spanish sentence reference. No doubt, ever answering doubt, it would never accept an argument on unknown person. So this is really very noisy. We can't make out the meaning much. And our translation produced, no doubt in answer that he would never accept a request of an unknown person. Request from an unknown person has become request of a unknown person. So there is a grammatical mistake here. It should have been an unknown, which is correctly produced in the baseline system. Okay. So many of these things are not really understandable, which is why explainability is becoming so important in all kinds of neural processing. Cannot explain many things as to why neural network is doing something. And then we tried zero-shot translation also, where pairs were completely unseen. Remember that the results so far was involving English, and the unsupervised neural machine translation was trained for English, German, French, and Spanish, where English is always there as one of the languages. Now here we report figures on zero-shot translation, whereby we see that Spanish, French, no pair has been, the machine has not been trained for this pair at all, English, Spanish, French, or Spanish, German, French, Spanish, French, German, then German, Spanish, German, French. Now, French, Spanish, we can see the blue score is above 10, and any score above 10 is really respectable, because we can start building things with that kind of blue score. And Spanish and French, because they belong to the same family, the family is called Romance family. Spanish Italian, French, and Romanian. These 4 languages belong to the same family with huge sharing of vocabulary and huge sharing of syntactic and morphological properties. Now, Spanish and German, you can see that the translation score is really low, just about 4.8. This is because Spanish and German are from different families. German belongs to Indo-Germanic family. Spanish belongs to Romance family. Moreover, German uses heavy compounding. Big words are formed using small words at constituents. So that problem also needs to be solved. Byte pair encoding actually goes towards solving those problems. So in unseen pairs also we do see, some good quality translation, many moderate quality, and many bad quality translations. So UNMT actually can deal with multiple languages, all pair translations, all pair zero-shot translation involving non-target language. Encoder really brings back the interlingual representation, and we have empirically observed that the machine makes better lexical choice. That is, it chooses more appropriate words compared to very small amount of parallel corpus used on a neural network. In fact, a neural machine translation, a small amount of parallel corpus is no good at all. It is as good as doing random translation. But this approach that we have shown with unsupervised neural machine translation many times achieves respectable blue score even in zero-shot setting. We did another piece of work on Anup Kunchakuttan, who finished his PhD with me and now is with Microsoft. So cross-lingual orthographic syllables for multilingual transliteration. This was a piece of work which made use of some linguistic property. So we came up with a measure called lexical similarity between pair of Indian languages, longest common substring ratio. Now, if we look at this table, the figures seem intuitive. For example, Punjabi and Hindi, the lexical similarity between longest common substring ratio, that means it is a measure of the shared vocabulary between the 2 languages. Now, Hindi and Punjabi are very close languages. We see very high level of LCSR value, about 68. The unit is not very important. So Punjabi has a lot of shared vocabulary with Hindi, little less with Gujarati, still less with Bengali, little more with Marathi, almost like Marathi for Konkani. Drastic drop for Telugu. Telugu is a Dravidian family language. With Tamil, still less. With Malayalam, little more compared to Tamil, because Malayalam uses many Sanskrit words and Punjabi also uses Sanskrit words. If I take any other language, let's say if I take Bengali, Malayalam overlap is 32. With Tamil, that reduces. With Telugu, it increases again, because Telugu uses many Sanskrit words again. Konkani and Marathi, these are also showing good overlap because they're all from Indo-Aryan family. So Chandrama, Chanda, Chand, these have common substrings for all these Indo-European languages. Dravidian will have a different language, different word for moon. So the network architecture is same as cross-lingual embedding generation and unsupervised neural machine translation architecture. Here there is a shared encoder and output decoders are for 2 different languages. So Tendulkar Hindi and Malayalam Tendulkar. right? These are the two different decoders. Now, the approach is very similar to unsupervised machine translation. So I'm concentrating on results. So this is completely unsupervised, no training data. We see that for the Indic family, we get pretty respectable accuracy figures like 37, 38 for transliteration. And substantial improvement is seen for accuracy over bilingual transliteration. Okay, so multilingual transliteration where languages help each other, and we are taking the string, breaking it into orthographic syllables, that is, syllable boundaries are at vowels. So that kind of syllable breaking and cross-lingual embedding on these orthographic syllables produces accuracies close to 40 for certain pair of languages. Hindi, Tamil, for example, 38.70. Now, transliteration accuracy being 40 is really not really, is no good. Transliteration is very critical for translation. So, and transliteration is not as difficult a problem as translation. So one expects an accuracy around 80 and more than 90. Now, Google Transliteration package is extremely good. Maybe you have used it for rendering text in Indian languages. Their transliteration system is really good. We have made observations for European languages also. So similar target languages. Polish, Slovakian, then Bengali, Kannada, English, and so on. So we do see transliteration accuracies around 50% for the Indian family, Indic and English, Bengali English, Hindi English, Kannada English, Tamil English. So the accuracies are in the range of 50s, except for Tamil to English, where I believe the data was small in amount, or not the data, where I believe the problem happened due to agglutination. And similar source language, we do see from English to Bengali, English to Hindi, English to Kannada, English to Tamil. And here the accuracies are really between 45 to 55. For English and Hindi, it is 60. So these are really lot of improvement over bilingual phrase-based SMT approach. We have conducted experiments for European languages also, and Arabic to Czechoslovakian, Slovenian, and so on. Okay. Now one interesting observation we made was that there was major reduction in vowel-related errors. So transliteration really suffers from voicing and unvoicing. Okay, so voiced consonant and unvoiced consonant, aspirated consonant and non-aspirated consonant. So tha and tha is confused. Tha is unaspirated, tha is aspirated. Ta and da, da is voiced, ta is unvoiced. Pa and ba. So this kind of confusion happens very frequently in transliteration, and also vowel-related errors. Now, a very interesting observation was Morris, M-O-R-I-S. When translated to English, produced M-O-R-I-S. This is valid, but Morris is more accurately written as M-A-U-R-I-C-E. And it was interesting for us to observe that our transliteration system could produce M-A-U-R-I-C-E, whereas baseline system produced Morris, M-O-R-I-S. Okay, so this happened due to the help from multiple languages. So this was an exercise in unsupervised transliteration. And between unseen language pairs, unseen source language, unseen target language, again, we obtained accuracies in the range of 40 to 60. Okay. So this was very encouraging for us that with very little or no data, one can attempt these problems. One can even attempt these problems because of the cross-lingual embedding. Okay, so a lot of numbers we generated in many kinds of settings. So, so the summary would be that neural cooperative natural language processing is an upcoming and very, very hot area of research. The foundation for this is cross-lingual embedding. Embedding can be of words and subwords. Subwords also can be embedded in a geometric space if we train a machine based on only subwords. And different approaches for low resource machine translation, subwording, pivoting, factoring, cross-lingual embedding. Pivoting, factoring, and subwording I covered in the first part of the talk on machine translation. Cross-lingual embedding is mentioned today. So the conclusion should be end-to-end systems are the future. We will not do a lot of analysis on the source side sentence and then pass the information to generate target language sentence. That will not happen. End-to-end systems are coming in a big way. Deep learning layers do the task of feature engineering and classification. That is the folklore, and we have to find out if really lower level tasks are shouldered by deep neural network layers. And cross-lingual word embeddings, they bridge the language barrier. So again, everything I said is linked from my homepage in the form of publications. And a lot of resources, tools are available from the CFILT, our lab website. Okay, thank you. And we can take questions. Hello?
Yes, sir.
Okay. So are there any questions, comments? Any questions, comments from anybody? Okay, so if not, then I'd like to end the session and thank you very much. Okay.
Thank you so much, sir, for your time.
Thank you.
Okay, so we will take a short break of 5 minutes and then we can move on towards the hands-on session. So you guys can start implementing your own empty system. And meanwhile, if you have any doubts or any errors or any question to address, I'll be present here all the time. So this is what we have to essentially do in this session. So this is the workflow. So you can pick a language and start customizing the reference code, or you can start building your own code from scratch.